Alright, so we're going to do another proof related to measure theory on the idea of the supremum. So lots of good proofs to be done here. There's lots of problems out there to be solved. And yeah, now if you're, if you're, part of the younger audience, this is going to come about a little bit confusing to you. So I'm going to try to work it out the best of my ability as I can. But, honestly, I would just, if you actually don't know a lot about these concepts, just enjoy the video, watch how the proof is done. I promise you'll get something out of it. And let's get started. So this is our first question. We're gonna have two in this video, two questions. Ooh. And we're gonna have a set A, cap A, and it's gonna be a non-empty set that's bounded above, and we're going to show that the supremum of cap A plus C is equal to the supremum of cap A plus C. Okay, so the plus C is going to be outside. Now this is very similar to this proof right here, which I've made the video on before, where the supremum of CA is essentially this question right here, where the supremum of CA is C times the supremum of A. And we're going to apply some kind of idea like that towards this proof, but we're also going to deviate from it a little bit. So let's first note some things, and we know that A is not empty, and so there must exist some little a within big A that's because we're given in the problem that A is a non-empty set, so there must be some element. And so we can then follow by saying that A plus C, right, is also in cap A plus C. Okay, nothing too crazy here. We're just making some pretty generalized statements. All we're doing is to this guy, we're just tagging A plus C. Okay. And it then follows, right? We have this little statement here, and this means that A cap A plus C is also non-empty. And this will come in hand. And now we're going to observe the fact that we also know that the supremum of A exists because it is bounded above. That's what we're given in this part of the problem. So the supremum of A exists, and more specifically, that is by the completeness axiom. And there's a lot that you're going to have to deal with if you want to figure out what this axiom is. Axioms are not very simple. They're actually super complicated, even though they're the foundations of mathematics. So do your own studying for this topic. And so from this, we can now make the observation that little a plus c must also then be less than or equal to the supremum of A plus C for all A within big A. And this makes sense, right? Intuitively, it must be less than the least upper bound. And with this idea, we can, which shows that A plus cap A plus C is also bounded above by the supremum of A plus C. Okay, we're just making very natural statements here. And so, and from here, and those of you that know, we can use the completeness axiom. So by the completeness axiom, the supremum of A, cap A specifically, plus C exists. Okay, or just by the completeness axiom, we're just saying that the supremum of cap A plus C exists, and so therefore the supremum of cap A plus C is less than or equal to the supremum of A plus C. Okay, so remember, up until now, just a quick catch up. We said that A is not an empty set, so there must be an element of A within A. So we're going to call that little a. And we noted that then A plus C must also be in cap A plus C. So cap A plus C is non-empty. So we just showed cap A plus C is non-empty. And then we observe that because cap A is bounded above, and that the supremum of cap A exists by the completeness axiom, we then describe that little a plus c is also bounded above by the supremum of cap A plus c, and therefore cap A plus c is also bounded above by the supremum of cap A plus c. Okay, that's all we're showing. And from here we can also then, some of you might have noticed that we can just simply write that little a plus c is less than or equal to the supremum of cap A plus c for all a within cap A. And this now implies that from here, just make that more clear. And this implies that little a is less than or equal to the supremum of a plus c minus c. So we just subtracted the minus with c from the other side. And this is still for all a within cap A. And I'm writing this for all a within cap A because it keeps the proof very stable and very steady. This is really important to be very careful when you go to graduate level mathematics or undergrad level mathematical proofs. Just be very careful. Okay. And this is really just saying that the supremum of cap A plus c minus c is an upper bound. I'm going to put BD for A. And so because of that, consequently, we can now say that the supremum of cap A must be less than or equal to the supremum of cap A plus c minus c. Now all that we can now say from here is we can move this plus, this minus c to the left and just add AC. And so the supremum of A plus C must be less than or equal to the supremum of cap A plus C. Okay. Now all we, from this step, right, and this is implied, all we did was just, do some couple of steps that led to this inequality, and combining these inequalities, we can now have the result that we were looking for, that the supremum of A plus C is equal to the supremum of A plus C. Okay, that is enough to show. And more specifically, the inequalities that we were combining, let me just see where I put them. So from this result, we are able to proof is complete, and we combined two inequalities from earlier. So the inequality that I'm just going to write it here because I'm too lazy to find it. So all we're doing is we're combining that the supremum of A plus C is less than or equal to supremum A plus C. We're combining this inequality with the supremum of A plus C less than or equal to supremum of cap A plus C. We're just combining these inequalities to make a formal definition. Okay. Second problem, as I promised to go over and give a solution to. So, if we have a same thing where A is non-empty and bounded above, I'm just going to say bounded up, and C is greater than 0, then we need to show that the supremum of CA equals C supremum of A. Now, I did this proof up here one time in the previous video, but I'm going to approach this problem with a different proof. and something that I think I personally like more. So we're going to do the same problem, just with a different proof, okay? And so the first thing we're going to know, again, is that A is non-empty, okay? It's not an empty set. And so, same thing, little a in A, it's an element. So that C times little a is also in C times cap A. So notice how, the reason that I put these problems together was we were able to take the proof for this one, the structure of that proof, and we can now apply it to this problem. And so therefore CA is also non-empty. Okay, awesome. So now we can take a look at the fact that A is bounded above. So we once again it's almost the same proof that the supremum of A exists by the completeness axiom. So all we're saying is that C times little a is also less than or equal to C times the supremum of big A. And this is true for all A within big A. Okay, so this is the same structure of the proof as the last question. Okay, and this is of course for C is greater than 0. So CA is bounded of, so CA with cap A is bounded above by C supremum of cap A. And so by the completeness axiom, because we know this is true from this earlier statement, we can now just go ahead and apply the completeness axiom, and we can say that the supremum of C big A exists, and more importantly, that the supremum of CA big A is less than or equal to C times the supremum of cap A. Okay, so that's all we're showing here. We're just giving an inequality, and I'm going to label this inequality 3. So keep that in mind. And of course we can do the same things, right? That C little a is less than the supremum of C big A for all A within the set. And we're going to multiply both sides of the equation. We're going to multiply it by C inverse. So multiply both sides of the inequality by C inverse, and we're really going to get just A is less than or equal to C inverse, or whatever you want to call it, C to the negative 1, times the supremum of C big A. Of course, for all A within big A. And consequently, all we're just going to do is just multiply, or not really multiply, but we're going to move some stuff around, and we're really going to get that the supremum of big A is less than or equal to the, we're going to say that's less than or equal to C inverse supremum of CA, because we just showed earlier that for C to the negative 1 greater than 0, we know that yields this, and from here we know that C to the negative 1 supremum of CA is an upper bound. It's an upper bound for A. And so that's how we can consequently get this part right here. And this really just implies that C times the supremum of A is just less than or equal to the supremum of CA. We're going to label this inequality 4. And so all you have to do is combine this inequality, similar to what we did, and this inequality, and we can see that because supremum of CA is less than or equal to this, and that's also less than or equal to that, if both of them are less than or equal to each other, no matter which place you put it, well, obviously that just means that C supremum of A, and therefore must equal the supremum of CA. So all we're showing in these proofs here is that if you have, 1 and 2 maybe for this, if you combine these inequalities, because they're essentially flipped, but the inequality sign is just not flipped, if one is less than or equal to the other, and the other is also less than or equal to the other, well, that just means that they're equal to each other. And that's kind of the intuition behind this proof. So yeah, there you have it. And my question to you guys for leaving this video would be, take a case for this second problem. I want you to ask yourself, what happens if C would be less than 0? What if C was not positive and it was negative? What would happen? And I want you guys to give your own proof for this if you want. I have a solution to this that's coming up. It's very simple. I might post it in a short. I'll link it obviously in the description once I see some stuff that you guys want to see. But yeah, that concludes the end of this video. And remember, this is hard. This is very hard math. But if you're a high schooler or you're young and you're interested in this kind of stuff, this kind of thinking, well, I hope you read some textbooks on this material, because this is really, really great stuff. So yeah, I'll see you guys in the next video. Thank you so much for watching.